Infinity is a bit much. Let's stop at some value lambda. That means that my Hamiltonian isn't a straight line from 0 to 2 pi, but okay, it's nearly that, it just behaves like this. Then I don't have quite the same system. I have a slight deviation exactly where theory is very important, which is near the ground state. This could be the Planck energy. So the Planck energy is so large that in ordinary quantum mechanics we don't reach such energy levels. We only stick to a region very close to where it's zero. So these are the lowest value of the Hamiltonian, but they are not so well represented by this formula, because this formula, if you cut it off, it looks something like this, and then the lowest energy states are here. That's not quite the same as when it would be a sharp corner. But it would be a sharp corner only if I take the sum to go all the way to infinity. And here's my problem. If I add to the Hamiltonian the evolution operator of an infinite number of steps, that's a non-local Hamiltonian. So a Hamiltonian does not quite reflect the locality of the system. However, the physics is entirely local. So now I have a funny thing, strange thing, the physics is local, but the Hamiltonian that I get out of it is not. And this is why the original idea, I think now, is running into some difficulties. You could say I should not have been surprised by that, because we don't believe that quantum mechanics has a classical origin like this. Well, I still do believe that, but you have to do something more clever. This procedure here doesn't quite work. We have to do something smarter than this. So if I take this sum converges too slowly, and it turns Hamiltonian into a non-local quantum Hamiltonian. So according to Hamiltonian, it looks like if I take time steps smaller than delta t, the things oscillate wildly, and after one passes delta t, it goes back to just one step. But that's non-local. And so I have a locality problem in turning this into quantum mechanics. So my quantum machine, the tool I want to use, suggests that the whole thing is non-local. That I want to avoid. So now the question is, can we do this better? And many people who do the foundation of quantum mechanics will be full of objections to what I'm doing. I don't care about that. I'll mention those objections after the break. So for the time being, I do this, but then I said, well, this Hamiltonian here is not very good. I'll do it differently. I'll take again the straight line. I'll Fourier transform it. I'll write it as a sum of sines and cosines, but I want that sum to converge in the middle here. It may be bad at the edges, but I don't care too much about the edges. They are half a Planck energy away from the origin. At the origin, it's much easier to take a straight line, Fourier decompose it, and it's composed of sines and cosines. The cosines are very small, or vanishing, and the Fourier transform here converges very rapidly. So whereas the expression of Hamiltonian in the edges here is very, very bad, the expression is very good at the center. Now, why did I not decide to sit at the center right from the beginning? Well, there's a problem here. H is positive at this end, and H is negative at this end. My Hamiltonian is not bounded from below. So, looking at quantum mechanics this way, the mystery becomes, why is it that the Hamiltonian has a ground state at all? The ground state seems to be sitting here. This is why I was interested at this point. But that's not the correct ground state. I want the ground state to be sitting here. But then the Hamiltonian is not bounded from below. So I have again a problem. I'm not the first to hit such a problem. The problem was encountered before, in fact, by Dirac, when he was looking at the Dirac equation. He had exactly the same problem. He was looking at the motion of the electron. He wanted the equation of the electron to be invariant on Lorentz transformations, and he found there's positive energy states and negative energy states. Now, Dirac was a genius, and he found the solution to that. His solution was second quantization. well, that is just nice. I think this, in the standard model, we have second quantization all over the place. So if we want this to generate anything like the standard model, we have to apply second quantization. And so what now we do is, okay, we say no, we don't have one such system. We have one such a system at every point in space and time, and a single particle is described by this, but I have an indefinite number of particles. In fact, I have particles and holes. So now, the question is, how do I introduce fermions in this world? And of course, I like fermions very much because it reminds me of this Onzaga Kaufman paper, where they used fermions to solve the icing wall. Say, yes, fermions. So, what are we going to do? Take a single particle and now describe, take again this Hamiltonian, but I'll call it little h. So psi t is minus e, is e to the minus I little h t psi 0. And little h is this, but I'm looking at the expansion around this point where the expansion converges where I only need a few ends, basically only one, and I already get a very accurate result. So that's much better. This Hamiltonian h is local, but it is not bounded from below. But just like the Dirac equation, Dirac also had a choice. Do I take a local Hamiltonian, then it's linear and it's very pleasing, or do I take a non-local one, such as the Klein-Gordon Hamiltonian, which is the square root of p squared plus m squared, but that square root gives you also the non-local effects. It's exactly the same problem. It is positive to be local. Dirac preferred the local one, and he had to do something about these negative energy states. And his answer was, I turn this into fermions, and I first diagonalize the Hamiltonian h here. I will get positive energy states and negative energy states. And now, being Dirac, he was very clever. He says these are all filled up with particles. I take an indefinite number of particles. So now I take the same model here, but now I actually could have used colored chalk. But anyway, if there's I say some of these particles are occupied, and some of these things are unoccupied. They are particles and holes. So when they're occupied, it's a particle. When they're not occupied, it's a hole. And all these particles evolve according to the same hole. So that hole is given by Hamiltonian, which is the same as the previous one, but I take an Hamiltonian little h. And now there's a little mathematical theorem which you can prove in a few lines, which is that now you can introduce, first of all, fermionic fields, psi n, where n is now counting the states in my machine. So psi n, well, first I define the operator phi n, which is the operator that either creates or annihilates a particle. I say phi n on a particle that has a particle there is state where a particle is not there. Phi n, if the particle is not there on the state n, is just simple. And this operator can be written as the operator 0, 1, 0, 0. If there's a particle, it vanishes. If there's no particle, it vanishes. If there's a particle, it produces the no particle state. And phi dagger is the opposite. So this is phi. Phi dagger would be 1, 0, 0, 0. And we have that phi and phi dagger anti-commute. Sorry, the anti-commutator is the identity. But at different spaces, phi n and phi m, where m is not equal to m, they commute the way it's defined here. That's not a proper fermionic field, but the solution that had been found by Gerard and Wigner long ago. The Gerard-Wigner transformation says that if I have a field phi at the point n, I multiply it by -1 to the power n smaller. And n smaller means I'm looking at all particles with a rank number below the position n, and I put a minus sign if there's a particle there. So I'm looking at whether the number of particles is even or odd. And if you do that, then this law turns out becomes an anti-commutator. And now you have, and I call that operator, I call that psi of n. So now I have that the anti-commutator between psi of n and psi dagger of n is delta nm, and the commutator is 0. The anti-commutator of two psi's itself is 0. So that is just a proper fermionic field. These minus signs are totally harmless in this particular example, but you have to watch out for this minus sign. Sometimes it's tricky. If you have an odd number of states on such a circle, you have to be a bit careful with this minus sign. If you go full circle, you might pick up a minus sign. I'd say that doesn't matter. This minus sign is physically harmless, but you have to know it's there. And then you have made a transformation. You've turned the thing into a fermionic field, and now I can write down a Hamiltonian as psi dagger h psi, where h and this n and this m, and h and m is now this little Hamiltonian which describes the evolution of a single thing in the usual way. So this now basically is a Dirac Hamiltonian for fermions. And now I can say, let's look at the ground state of this Hamiltonian. The ground state, the lowest energy state of this, is where all these negative energy states are occupied and the positive energy states are empty. There's no state with low energy in that. And the nice thing about that is that the first excitations of the vacuum are now states which excite things from the middle somewhere to a small position elsewhere. They're not exciting these very many states. There's one thing here you have to watch out for. That's only a measure zero set of states, so forget those. I'm basically concerned about what happens here. This is a good and local theory, so now I've recovered locality for this system. And now I want to make one more step, and that is, now I know in principle what I want to do. Let's try to get a more interesting example. Example that looks physical. Unfortunately today I'm not looking at very physical equations, but what I'm going to do now is as close as physical as I can get. I'm going to describe neutrinos. Between quotation marks. Why between quotation marks? These are idealized neutrinos. They are totally massless, not approximately massless like the neutrinos you know all. These are exactly massless and they're totally non-interacting. So a very dull system indeed, non-interacting neutrino-like particles. Why do you call them neutrinos? Well, you obey Majorana equation, or in this case I can replace it by the Gerard equation and say the Hamiltonian for a single neutrino is just p dot sigma, where p is the momentum, the displacement operator, and sigma is a Pauli operator. So the sigma 1 is 1, 1, sigma 2 is minus I, and sigma 3 is 1 minus 1. And you take the inner product between the momentum and the sigma operator, and that is the Hamiltonian of the two components massless neutrino. When it's massless, it doesn't get mixed with antineutrinos and all that. So it would be either a Majorana or a wire neutrino. If massless, there's no difference between those. And these are Pauli matrices. And this, actually, I should call this perhaps little h, because I've been using the word little h for a single first quantized particle. In the very end, I will again go to h equals psi bar little h, or psi dagger little h psi, and that is of course the Dirac Hamiltonian, but now for massless neutrinos. in a somewhat different notation than we used to, because the mass says only have 2 helicities rather than 4. Let's say a single neutrino is either completely left-handed or completely right-handed, but I don't take the 2 of them, only a single one. So actually, if I flip a sign here, I turn from left-handed neutrinos to right-handed neutrinos. Those say these things are right-handed, their antiparticles are left-handed. So that's the 2 neutrino types I'm now talking about. But what's nice about this is part of the standard model, although only a small part. But in principle, you think of beginning, building up a standard model, starting from these objects and then continuing. So I'm only at the very, very beginning of the standard model. And this system is interesting. It is, of course, a quantum system. You'd not talk about neutrinos as if they are classical. Now I'm saying, however, yes, they are quantum mechanical objects, so I describe them as if they are roughly like this. But for these neutrinos, I can identify what happens at this level. And that means for neutrinos, I can define what I call beagles. In honor of John Bell, beagles are operators B(I) of t. Think of the Heisenberg representation where the operators are time dependent but the states are not. Then you can consider operators B, which are a function of t, and they evolve with this Hamiltonian. Now the question is, can I find operators such that they all commute at all times? Bi of t and Bj of t prime vanishes at all t, t prime, I, and j. Now, this is a blasphemy in terms of ordinary quantum mechanics. People would say you never have such operators. Well, for these particular objects you have. Write them down for you immediately. What is operators I? And then I can make this mapping from the classical system to the quantum system and back. What's nice about this neutrino is that time is infinitesimal. Delta t is an infinitesimal time element, so at first sight you don't think that you get that difficulty. And well, I can identify these beagles and then go over to the Gerard picture afterwards. And the beagles are highly interesting and they display properties of the neutrinos which you might not have realized when you first encountered them. The beagles of a neutrino, let me write them down. I write down the momentum operator P as a vector as a PR times a Q. Q has a hat on it. Here the hat means it's a unit vector. So Q hat squared is by definition the identity. And PR is just whatever it deviates from. So PR could be the absolute value of P. Then PR is always positive. Now I want a description of PR is positive or negative, so I put a constraint on P hat, saying that the third component of P hat is positive. So, Q hat is the orientation of the momentum P. So here goes P. Q is just a vector of unit 1, of length 1 in that same direction, or if P goes in that direction, Q is also in the same direction. So Q is the orientation of P modulo its sign. And that is my first beagle, is Q hat. Here's the momentum, only the orientation of momentum modulo its sign. Then I have, as a second operator, Q hat dot sigma. I have 3 Pauli matrices. They, of course, are not commuting, so I can only take one component. I take one Pauli matrix, the one which goes in the same direction as in the direction in which the neutrino is moving. I call that S. And my third variable is a bit more complicated. It's called R, and R is 1/2 Q hat dot X plus X dot Q hat. The problem is X does not commute with P hat. X is a vector. It doesn't commute with P hat, so I take the average of it, it's telling in front, it's telling behind. This way R is Hermitian. So R is basically the position in the direction of Q hat. And now comes a beautiful mathematical theorem. These three, Q hat, S, and R, are beables. They all commute. It's a fairly elementary exercise you can do on the back of an envelope. The most difficult question is whether Q hat and R commute, but S commutes with Q hat is obvious because S doesn't contain anything that could not commute with Q hat. So, but the more delicate question is whether R commutes with Q hat. But actually, that question is not so difficult. R is the X operator in the Q hat direction, but X is, of course, the translation operator in momentum space. And Q hat of X is a dilatation operator in momentum space. The dilatation operator says what happens if you blow up the scale, if you reduce the scale of things. And the commutator between Q hat and R tells you how does Q change under a scale transformation. Well, ladies and gentlemen, Q hat has 1, 1. It doesn't scale under a scale transformation. Therefore, Q hat commutes with R. So R commutes with S, that's trivial, because, well, there's nothing in... Oh, R commutes with Q hat, therefore it commutes with... And R commutes with sigma, therefore it commutes with S, and everything else commutes. So these are beables. And not only they commute at all times, because now you can say the ddt of Q hat is 0, it's a momentum. Ddt of S, well, if you look at the Hamiltonian, it's P sigma, so the Hamiltonian is Q hat PR sigma. Q hat sigma was S, and S commutes with PR, so the ddt of S is also 0, and the ddt of R is S. And since S and R and Q hat commute at time equals 0, they commute at all times. So this is a complete set. It turns out to be a complete set of beables. And you might think that this is simple, but it's not so simple at all. Because I asked the question, okay, if I have the usual basis of states for quantum mechanics, for a neutrino, which is the axis, the Pauli matrix sigma 3, then that would be a convenient basis, or momentum space and sigma 3, that could be a convenient basis. How does this basis transform into the basis where I have those three? So I want the basis where I fix Q, S, and R. Well, Q is in momentum space, R is in position space, so I have a fairly non-trivial transformation between these states and this. But still, it sounds like something that you can do just very easily in the back of the envelope. Well, this is in case it tells you what the X operator is in Q space. And it's not a simple expression. In fact, this expression is also very condensed. I haven't yet said what L ont is and what theta and phi are. S1 and S2 operator. It is a complicated expression. The X operator does not commute, it's not a beable. The action of a particle does not commute with its P, not commute with Q hat, and so on. So this is not a beable, but it's just an operator which you can calculate out of the beables. And I just gave the answer not intending to derive this, because that would take me half an hour. But, so it just shows that this is quite complex. But it's a beautiful system. I like it very much. I had some trouble deriving this equation. I made some errors in the beginning, so to smooth them all out was not so easy. And I also have a 1 over PR operator, which means there's a menace of a singularity when PR goes to 0, and so you have to integrate. PI is a differential operator, so one of PI is the integration operator. And you worry about boundary conditions. That turned out to be a mild problem in here that I had to work out, sit carefully, do it correctly, and this was the expression I end up in my calculations. So it's not so easy, but this is a beautiful example of a system, and now we can go on from there. Before the break, I just want to show you what's the physical interpretation of this. What are these beavers? How would I formulate the theory of beavers to start off with? Well, look at what they do. Q hat tells you there's an orientation, a vector pointing in a certain direction. That's roughly the vector in the direction in which the neutrino is going. It's going with the speed of light because it's massless. What's R? R is a position in that same direction. So actually you have a sheet orthogonal to this thing, and R is the distance of the sheet from this point. It doesn't say where on the sheet the neutrino is sitting. The neutrino could be sitting anywhere on the sheet. So Q hat actually describes a sheet, and R describes the distance of the sheet from the origin. S describes in which direction the sheet is moving. The sheet could be moving in this direction or in that direction. So a sheet is moving with either sheet like this, infinite sheet, it moves with the speed of light, either this way or in that direction. In fact, I introduced operators S1 and S2, which flip the sheet into a sheet that moves in this direction, into a sheet that moves in the other direction. Of course, that S flips sign when you rotate 180 degrees. That's characteristic of a spin 1/2 particle. So think of a classical ontological system of sheets moving in speed light in one direction or the other direction. You have a rotation of 180 degrees which flips the sign. Do twice rotation, you get back to where you were. That's characteristic for a spin 1/2 particle. So you can see that an infinite sheet, already physically speaking, is related to spin 1/2 objects. And but it's infinite, so it's not quite local. So I'm abandoning some version of locality in this theory. Actually, the theory is local, but I can't introduce any local interactions. That's where the theory becomes right. So this is not the end of the story, it's only the beginning of the story. And how to turn this into a standard model with interactions and with gauge fields and everything is still a hell of a problem which hasn't been solved. But you see what kind of philosophy I like to employ in quantum mechanics, and after the break I'll now discuss that there are some very, very good things about this view of quantum mechanics and some things that are quite horrible and awkward and difficult to understand. And I'll try to discuss both of them just after the break.
If I understood correctly, you introduced sort of quantum of the time anyhow, because your system of states was disparate, right?
In the simplest case, I have time discretized, so time is quantized.
So you need some quantum of the time.
Yes.
But how you know that if you consider many subsystems, this quantum of the time should be the same for all the characteristic transitions? So you're postulating it in some way, right?
Of course, later on things of general relativity, where time depends on geometric and so on. So this will be a problem. But you can also say, well, I'm only looking at the state nature is in, at the discrete time, but I'm simply not looking at time in between. So the value of delta t could depend on your description, and I'm not too much concerned about this, certainly not at this stage of the investigation. Later, we have to worry to write down B-rolls, and the B-rolls are only defined at integer time steps. What those time steps exactly are is something that will have to be sorted out.
I meant if you are an observer, if you want to detect the result of the experiment, you have
So
to measure this time.
You would think of having a comb, and thing hops from one tooth of the comb to the next tooth of the comb, and the states